We're starting on problem A on page 1 of the notes. So what's different about these problems is we have variables under the roots, but we also have different numbers in the crevice of the square root. So I've got a little 4 there, got a little 3 there. I've got a little 3 in this one and a little 3 in that one. These little numbers are called the index of the radical. And it tells you what root you are taking. Now you'll notice in problem A, we don't have a crevice number. We just know that this is a square root. I want you to write a little 2 there. Square roots have an implied index of 2. And if you're like, why don't we write that little 2 all the time, Mrs. Cairo? It's because we're lazy. We don't need to. It is implied because in all other math applications, square roots are the most common ones we use. So it's kind of similar to how if I have the variable x, that has an implied power of 1 and an implied coefficient of 1. So when I just have a radical with no index number, we assume that index number is 2. And putting that 2 there is going to be helpful to us as we start doing our rules with our variables. So if I have the square root of x squared, the implied index is 2. What do you think the square root of x squared is? It's just x. When I take the square root of 9, I'm saying what times what gives me 9? The answer would be 3. So if I'm saying the square root of x squared is what, I'm saying what times what gives me x squared? Just x. So the square root of x squared is x. The cube root of x cubed is also x. And the fourth root of x to the fourth is x. So if we look at our number correspondence with this, we did talk about cubes back in, was that unit 5, when we were talking about sum and difference of cubes for factoring. And we said that 8 is a perfect cube because 2 cubed gives me 8. So as we start doing roots, we would say the cube root of 8 is 2. The cube root of 27 is 3. The cube root of 64 is 4. So that's kind of interesting because 64 is not only a perfect square, it is also a perfect cube, and it is also way over here, a perfect sixth. So going back to our variables, you might notice a pattern. When I am taking a root of a variable, we can simplify it by taking the power of the variable divided by the index of the radical. 2 divided by 2 is 1. 3 divided by 3 is 1. 4 divided by 4 is 1. So for variables, we take the power of the variable divided by the index of the radical. There's our next big rule. And I actually want to go back to that acronym from Unit 5. Do you guys remember MAD SPAM? MAD SPAM was all about bases and exponents. If I'm multiplying bases, I add them. If I divide, I subtract them. If I'm powering up, we multiply them. Now, powering up was like squaring and cubing and taking something to the 4th power. So what about if I power down or root something? If powering up is multiplying, what do you think powering down or rooting does to the exponent? It divides it. So this is our new part of MAD SPAM. So now it's MAD SPAMmered, I guess. MAD SPAMmered. That sounds like a verb. MAD SPAMmered. So we've got rooting that leads us to divide the powers. Power divided by the index, or what we are rooting by. So let's go ahead and look at problem 8. We first identify the index of the radical, and we see that it has an implied index of 2. So that means I am trying to take the square root. So what's the biggest perfect square I can take out of 32? 16. So 16 is the perfect square factor. 2 is the non-perfect square factor. So that's how we are breaking up the number aspect of this. So 4 and 2. Now for the variable, I don't have to break this down into factors because since I am rooting, I can divide the power by the index. When I carry out that operation, my new variable power comes to the outside. So when I take the square root of 8, or what times what gives me x to the 8th, we would get x to the 4th. And notice that it is on the outside of the radical. Now, order-wise, this is not so great because I've got the 4, which is outside the radical, and the x to the 4th, which is on the outside. So since these are all joined by multiplication, I'm going to shuffle it so that the coefficient is first, the variable is next, and then we have the square root of 2. Now, in our final answer, we don't have to put that index of 2 back in because it is implied. So that is our final answer. We're going to go ahead and move down to example C next. We first identify the index of the radical. This is a cube root.
Would Olivia want to count T using the attendance office?
So I don't want to break 27 down into 9 and 3 because 9 is a perfect square. We instead want to look at our cubes column, and we see that 27 is a perfect cube. So what is the cube root of 27? The cube root of 27 is 3. So 27 is a perfect cube, and the cube root of it is 3. Then I look at my y's. I've got y to the 12th, so mad spam word, we're rooting, so we divide. Power divided by index gives me y to the 4th on the outside. Now z to the 7th. Ooh. Z to the 7/3. Does that please and sparkle? Do we like that? No, it's useful. We're going to get into fractional exponents a little bit later in this unit. But as far as simplifying goes, z to the 7/3 does not look great. For something like this, we are going to break the power. Similar to how we broke up our numbers into a perfect square and a non-perfect square factor, we want to break this up into something that is divisible by that index of 3 and whatever is left over. So what's smaller than 7 that's divisible by 3? 6. So we're going to break this down into the cube root of z to the 6th. That's going to be my perfect cube because 6 can be divided by 3. And then what's left over is the cube root of just z to the 1st or just z. So we have to identify the root we're taking from the beginning. We also have to show the root in any subsequent work. So got to show what root we are taking. We got to show that index number. So now that I have this broken up, what is the cube root of z to the 6th? We take power divided by index, and we get z squared. So I have 3y to the 4th, z squared, and then the cube root of z. I can't break this down any further because how many z's do I need to be able to take the cube root? 3. We need 4 of something to take the 4th root. We need 3 of something to take the cube root. So this is as simplified as we can go. Ooh. In big letters by this problem. Don't Forget the, any guesses? The index. We have to have that little crevice number there because the square root of z means something entirely different than the cube root of z. So a lot of times, this is the biggest mistake that I see on this test is messing up the index of the radical. So don't forget the index. So let's go ahead and skedaddle back on up to problem B. We've got the fourth root of 16. So fourth root means I'm looking for perfect fourths. Is 16 a perfect fourth? Yep. What's the fourth root of 16? 2. So 16 is a perfect fourth. The fourth root of it is 2. Then I've got my variable, a to the 24th. Power divided by index. It goes in evenly, so there's no need to break the power. So a to the 6th. Now b to the 13th. I do not want to have 13 fourths. We want to break this into a power of b that is divisible by 4, but is smaller than 13. So what's smaller than 13 that I can divide by 4? B to the 12th. And what power of b is left over? B to the 1st, or just b. Notice that I'm including that crevice number, the index, showing that it is the fourth root. So then we get 2a to the 6th. Power divided by index, we get b to the 3rd. And then the fourth root of b. Making sure we have that number inside the radical. Any questions on those two problems? On why or how we're breaking the power or how we're handling the variables to simplify them? All right, let's go ahead and take a look at problem D. So on this one, we are multiplying two cube roots together. Now, on all of the other problems, we have said simplify first. Try to simplify the radicals. But the cube root of negative 12, is 12 a perfect cube? Ooh, no. The cube root of A, that's not a perfect cube. And the cube root of b to the 4th, I would have to break that power up and then simplify it. When you are multiplying, sometimes it's best to wait to simplify at the end because sometimes when you multiply, you create more perfect cubes, more perfect fourths, or different pairs of numbers that create perfect squares. So we're actually going to multiply first here, multiplying my coefficients together on the outside. 5 times 3 is 15. Then underneath the cube root, and I'm going to make sure I put that index there, negative 12 times 18, woo, is negative 216. What's a times a squared? A cubed. Ooh, we just created a perfect cube. B to the 4th times b squared is b to the 6th. So here's mad spam coming back to haunt us. We are multiplying the bases, so we add the exponents. B to the 4th times b squared gives me b to the 6th. Now that I've carried out the operation of multiplication, now we want to try to simplify the radical. Now, before we do that, we've got to talk about an important rule that is different from what we have seen in previous units. What's the square root of negative 1? When we saw this in the quadratic formula, what's a negative under the square root mean? It means I. Why is the square root of negative 1y? Well, because this is essentially saying what squared gives me negative 1. And we find, well, no, just regular number squared will give me a negative. So I squared is defined as the square root of a negative 1. So I is what goes in here to make this true. So if I say what's the cube root of -1, this is asking what cubed gives me -1. And the answer is not I. I squared times another I would be -I. So I cubed is not going to give me -1. What cube gives me -1? -1. So we have something different here when we have an odd index radical. With an odd index, negatives come out as negatives. With an even index, like a square root or a fourth root, negatives will still come out as I. This is a very tough habit to break because anytime we've used quadratics or radicals in the previous units, we have always taken out negatives as I. But on this problem, here's our rule in action. When we take the cube root of that negative, the negative comes out as a negative. So this becomes -15. Then I look at 216. Is 216 a perfect cube? We see on our yellow sheet that it is. 216's cube root is 6. When we bring it out, whoops, we are multiplying those, but we are not putting it back under a square root, Mrs. Cairo, so we're going to get rid of that. And this is just times 6. Then what about the cube root of a cubed? Power divided by index, we get a on the outside. Power divided by index for the b. b6 divided by that index of 3 gives me b squared on the outside. So our final answer is -90 ab squared. I had a nasty set of cube roots that I was multiplying together, and I end up getting this nice simplified answer. Any questions?
Can I go small so we come to the other topic?
Before we go into the go to the homework packet. There's a problem that we need to change. Number 51 on the very back page. Change that 2/3 power to be 3/2. So on number 51, change that 2/3 to be 3/2. And on the front side, now I'm going to show you what to circle for homework. The first page of homework is not going to be due until tomorrow night, but you will want to try to get all of these circled problems done tonight. So go ahead and circle number 1, number 2, number 5. So 1, 2, 5, 6, 7, 10, 11, 12, and 13, 16, and 18 and 19 on the next page. So essentially you're skipping all the division ones. So I'll read those off again. 1, 2, 5, 6, 7, 10, 11, 12, 13, 16, and then 18 and 19. Folks, you have the rest of the time to work, and we're going to go outside. You can leave your stuff in here if you want.